Can you hear me? Yep. Okay, morning everyone. As Tur said, me and my colleagues from Algorithmic, Anton and Walter, who are also in the room, will be presenting some topics on quantum chemistry on near-term quantum devices. So first of all, we are from Algorithmic. So it's a company, startup based in Finland. And as the slide says, we want to harness the power of near-term devices to work on life science problems. So our work is summarized in this slide. So we want to use what we call quantum network medicine. So try to use quantum devices in the near term to extract information on disease networks and harness the power also of quantum chemistry to figure out better hits for potential drug targets and improve the drug discovery pipeline. So this said, as you have heard yesterday and the day before, we know that quantum computing is evolving quite quickly. There's a lot of hardware being produced in different parts of the world by different vendors, different techniques to build qubits. A lot of money is being invested in this, whether it's whole hype or there's something real that's still out for the jury to decide. But drug discovery, at least in our view at Algorithmic, is emerging as a promising area of application. And this is because there are things that can be done already on near-term devices, despite all the problems that these devices have. So this you have seen already. So if you imagine that what we're going to talk today mostly in our section is quantum chemistry. So if you want to describe a large molecule at the quantum chemical level, so solving the time-independent Schrödinger equation, the amount of classical memory that you will need will scale exponentially with the number of electrons, number of orbitals that you want to treat. While if you have access to a quantum computer, this will only scale linearly with the amount of orbitals. So this is quite advantageous because you can think that you can do larger and larger system without having an explosion in the amount of computational resources that you need. So why is it advantageous to use a quantum computer as a quantum physics simulator? So an arbitrary state of the qubits can be described, as I said, in an amount of memory that scales only linearly with the number of orbitals that you want to treat. So of course, a universal quantum computer can solve problems that are beyond the reach of simple quantum simulation or any classical computers, for example, factorization. But to do that, the estimates that we have nowadays is that you would need millions of physical qubits to be able to have error-corrected qubits, or logical qubits that are not affected by noise, and also circuit depth that is in possibly the billions of gates. So coherence times are extremely long. So in the near term, we don't have error-corrected qubits. So what we would need is probably around 1,000 of qubits in the next 2-3 years, if we trust IBM's timeline, and a depth that can be in the thousands of gates. So this means that we cannot possibly do factorization, but there are things that we can do in the near term, for example, quantum chemistry. So this presentation is divided in 3 parts. So there's one part that I'm going to present on the variational quantum eigensolvers, so the basic principles of how this algorithm works for quantum chemical problems. Then Walter will present a part on generalized quantum measurements, and finally Anton will show something about other techniques for state preparations that go a little bit beyond the basic principle of the VQE that I'm going to present. So the general problem statement, and I'm a quantum chemist by background, not an expert in quantum information theory, so that's why I'm taking care of this part, because this is what I know best, I would say. So assume that you have a molecular structure that is given. So you have a set of positive charges and a number of electrons in space. So you have the geometry fixed. And for that, you can write classically down the Hamiltonian for this problem, so for the electronic structure problem. What you want is determine possibly the ground state energy of this system, so finding the lowest eigenvalue for this Hermitian operator for the Hamiltonian. But also, it's interesting in many cases to know what happens if I stretch the geometry. So if I change the positions of the nuclei, this capital R, what happens to the energy of the system. So this amounts to diagonalizing this self-adjoint operator. But even though we can write the Hamiltonian pretty easily, classically down, and also calculate it in a basis of selected functions, it might take some time to calculate it, but it's not exponential, at least the time to do that. The representation of the wave function itself, which is what we need to calculate expectation values, for example, the energy or a dipole moment or a polarizability, which are quantities of interest for chemists, lives in a high-dimensional vector space. So it's a Hilbert space of the n particles, of the n electrons in the molecule. So you can imagine that as more particles are added, this wave function becomes increasingly more complex to represent. Of course, chemists and quantum chemists in particular have been at this problem for many, many years. So we went from doing calculations on pen and paper to program some of the largest supercomputers in the world to run these calculations. But the problem is still very, very difficult. Okay, so this is the water molecule. And what you usually do, you do a calculation to find some sort of reference state, which is easy to represent on a classical computer because it's a single determinant, so a single function in a very large Hilbert space. And that is built up in so-called occupation number representation. So you take a set of reference orbitals. So these are one particle functions, the one that I'm showing here on the right. And you have some that are occupied in the ground state. So there's pairs of electrons that live in each of these blobs of density in space. And then you have an orthogonal complement to that, which are unoccupied orbitals that you can use as degree of freedom to describe other configurations in the system. And any wave function that is viable for the water molecule is described by saying, is this orbital occupied or not in this given configuration? And this is the occupation number vector representation. So in the ground state or in the reference state, you assume that each of these ground state orbitals, the one that are in the red box, are occupied by one electron. That is called the Hartree-Fock reference determinant and can qualitatively describe pretty well many situations in electronic structure theory. However, the real wave function, the true wave function of the system, is a linear combination of all possible occupation number vectors. So you take one electron from one of the orbitals that are occupied in the reference and you excite to any of the other ones. And if you take pairs of excitations, triples of excitations, and take a big linear combination of all the possible excitations that you can generate, then you get to the true wave function. Of course, the coefficients in front of all these possible basis functions in the n particle space are unknown. And determining those is what would scale exponentially in principle, because you have to diagonalize an extremely large matrix in a basis that grows exponentially with the number of electrons in the system. So this is classically intractable. Of course, again, quantum chemists, and not just because I'm one, are pretty smart. So there are ways to approximate this problem. There are many things that you can do classically, for example, quantum Monte Carlo, or a different way of writing this linear combination of determinants. But let's see what a quantum computer can do for us, because in principle, they're pretty good at representing this growingly enormous space of basis functions of occupation number vectors. So in the variational quantum eigensolver, the basic idea is that you have a quantum computer and a classical computer that work in tandem together. So the quantum computer does what it's good for, so representing a state of a quantum system, so these occupation number vectors. And the classical computer will optimize some parameters for the circuit that represents these occupation number vectors. So you start with preparing some sort of quantum state on the quantum computer. And we call this an ansatz. And it is a variational form in the sense that we parameterize the gates in the circuit with certain parameters. And they're usually called theta because they're angles, as you've seen yesterday and the day before. Every time that you need to do something with the qubit, you represent it as a rotation in the space of the single qubit or in the space of two qubits if you're using two qubit gates. So the gates in the ansatz have these three parameters that were free to vary in a way that let us reach the lowest energy for the system. So for each value that we input for the gates, we prepare the circuit on the quantum machine, and then we measure. Okay. So at the end of the circuit, we have this barrier where all the qubits is measured, and we do this many, many times, of course, because this is probabilistic. So we need to take a certain number of shots to have an estimate of the expectation value of an operator, in this case the Hamiltonian, to get the energy, for the given set of parameters. And given that, yes, we are using a unitary representation, since this is a quantum computer, the variational principle still holds. So whatever energy we get as an estimate out of measuring this circuit will be greater or equal to the true energy of the ground state. Then we can use the fact that we have a variational estimate, so an upper bound to the energy that we can get, so that we measure the energy and then tweak the parameters in a way that the classical computer will suggest us. So we update the parameters, we update the circuit, measure again, and repeat this cycle until we get to a stationary point in the potential energy surface of this wave function ansatz. So the quantum computer essentially represents the state as a superposition of all the possible occupation number vectors, and the classical computer basically tells how to update the parameters, which in the occupation number vector representation would be the coefficients in the linear combination. So the optimization is purely classical, while the upper part of the diagram is done on the quantum computer. So this is in a nutshell, like very, very short, and there are many knobs that you can tweak here, and not just in the classical optimization routine. So the Hilbert space is an enormous space, even when you decide to cut down on how many orbitals you can have excitations in between. So you need to find a way to reduce the number of qubits that you want to use, and also the depth of the circuit that you want to use in your variational ansatz, because quantum computers are error prone. So if you keep adding more and more gates, if you are beyond the coherence times, then I mean you're basically measuring noise. As I said, not many qubits are available. So even if in principle you could do full CI, so considering all excitations from all orbitals to all other orbitals, you cannot in practice do it because you have limited resources on the quantum computer. So what you usually do are so-called active space methods, where you select a subset of electrons and orbitals that you want to correlate. And the simulations can be time consuming. And by time consuming, I mean that every time that you need to repeat the circuit and you need to do many, many shots, it takes time. So like the communication between the quantum and the classical processor is not instantaneous. And measuring is also not instantaneous. And then you need to reset and re-prepare the circuit and measure again. So, and there have been some papers in the recent past, I think last year, also this year, where there have been estimates of how much like wall time it would take to run this kind of loop of classical and quantum optimization. And it doesn't exactly look good. And this is also because it's difficult to work with this machine. There are some, at the moment, fundamental limits on how fast you can do these operations. So let's look at the different steps quickly. So the state preparation, how do we get the circuit? So in the original VQE presentation, what you would...
Can I interject with just a quick question here from HackMD? So how do we know that the ground state was reached?
Well, I mean, if you can compare with the classical simulation, you can look at the error. But so I mean, even in a full CI calculation done on a classical computer, there is always a residual error that remains. You can never know that you are at the true ground state. Of course, the answer is in the experiment, but like experiments do not measure the absolute energy of the ground state. You would see differences between excited states, and then you would compare with that, for example. Yeah, so even in a classical simulation, there are residual numerical errors because there are always numerical procedures. So a full diagonalization is subject to the errors that come from using double precision floating point arithmetics, and the fact that you're calculating the integrals with the threshold that is not tight enough and all of that. So you can, I would say you can never know that you have the exact energy, and you can know that you have the exact energy only if you're doing H2, like hydrogen molecule in the ground state, because then you can do extremely high precision things in yes.
So basic question. So is the idea to represent the occupation of each single particle basis functions with a qubit?
Yes.
Okay, but so how do you ensure that you're in the physical n particle space? So if we do that, in principle, you have all occupation number.
Yeah. So I skipped some stuff, but so the single particle space, you take a tensor product of it, and then you take anti-symmetrized tensor product and anti-symmetrized products of that tensor product space. And this is the space of later determinants, which ensures that you are in the physical and particle space for the system. And there's a mapping between the Hilbert space made of anti-symmetrized and particle tensor products and the occupation number representation. So they are one-to-one. So you can represent each single particle state as 1 or 0 and still be sure that you are in the proper anti-symmetrized and particle state of the system. You can have other sectors of the Fock space. That's not the limit. So like if you actually do it on the quantum computer, sometimes you need to put a constraint, like a penalty operator, additionally to the Hamiltonian, because the Hamiltonian in that case doesn't know if you are in the n particle sector n-1 or n+1, because you really work in Fock space. You don't work in the Hilbert space anymore.
Space of
yeah,
the
yeah,
qubits,
no, yeah, correct,
correct.
Sorry, I misunderstood. Yes.
Of the variational.
Yeah.
Okay, thanks.
So you have all sectors in the Fock space. Yeah, correct. More questions from the HackMD? Maybe no. Okay. So let's look at the various boxes that I had in the diagram. So how does state preparation work? And Anton will tell us more at the end. But in the original prescription of the VQE, like the ideas from conventional computational chemistry were borrowed from the couple cluster method. So you have a reference function, this 0. This is a single Slater determinant. And then instead of building a linear combination by a sum with coefficients, you apply an exponential mapping to it. And this has some advantages, for example, size consistency. And this T operator is made as a linear combination of cluster excitation operators. So essentially you take one particle at a time, 2 at a time, 3 at a time, and you excite them from a certain set of occupied orbitals, these I's, to a certain set of unoccupied, the A indices. So this is not unitary, so it doesn't really work on a quantum computer because everything is unitary there. Everything has to be reversible. So what you do is you take the unitary variant of the couple cluster, where at the exponent of the mapping you have the cluster operator T minus its adjoint. So classically, this is something that it's extremely hard to make work on a classical computer because you get non-truncating expansions of the exponential. So it's pretty gory. But on a quantum computer, you don't really care because you're going to implement everything as a physical gate and then measure at the end. So you don't have to develop the formulas or try to write the gradient explicitly, everything that you would need to do on a classical computer. So usually you truncate to single and double excitation. So you take at most either one particle and excite or 2 particles at a time and excite. This is not exact, but it's potentially exact. And there's a lot of literature in the quantum chemistry side of things that has discussed whether this is going to get you the exact state or not. We're not going to go there. And finally, this is applied in trotterized form, meaning that instead of applying the full exponential, we take small time steps and apply products of exponentials. So this is an approximation in principle, but it can be made exact if you make the time step really small. And then you need to measure the energy. Okay, now we have the circuit. So imagine that we have this unitary couple cluster parameterization with some free parameters, and then we need to measure at the end. So to do this, you map the Hamiltonian in qubit space. So we started with the Hamiltonian in first quantization, where you had the different terms, electron-electron interaction, electron-nuclear interaction, kinetic energy. And now you take that, you represent it in second quantization as an intermediate step. So you write down some integrals that the classical computer can calculate really well, and I would say reasonably fast for you. And then you map them in qubit space, which means rewriting the operators as tensor products of Pauli strings. So there's a one Pauli operator for each of the qubits in the system, and then you take all possible tensor products with coefficients ck there. So now the number of operators that you might need to measure can be extremely large. But in principle, this is not a problem, because instead of having to write this expansion of the wave function explicitly and then trying to evaluate the form of this unitary operator, unitary mapping applied on it, and so on, you just measure each Pauli string. You have the state, and then you measure each of these pKs in it. And once you have that, you do the linear combination, and that's your energy. So while on a classical computer, writing the wave function would be an incredible task. On the quantum computer, you just measure at the end. You don't need to have the explicit form of it. And here comes the problem, one of the problems that you have with this way of doing things, which was the screenshot that I had from that paper when it comes to the time of executing each circuit and measuring, is that each of these strings needs to be measured on the same state. And each of these needs to be repeated many times. You have to take many shots for every string just to make sure that you have an error bar on it that is small enough so that you can trust the results. And every public string in principle needs to be evaluated independently because they do not commute with each other. So if you're not smart, you're ending up measuring in principle n to the 4 operators, each of them many times so that you get a small enough error bar. So, and the estimates for this, and the n to the 4 is because we have a quantum chemical Hamiltonian. Other Hamiltonians might be better or maybe worse. So the error in the estimation, so if you want to have a given epsilon, you have to use a number of shots that can scale with the power of 6 with the number of terms in the Hamiltonian. So and this places really a large constraint on what you can practically do with this kind of methods, because as I said, resetting the circuit and re-executing and measuring can take up to milliseconds. And then if you need to repeat these hundreds or thousands or hundreds of thousands of times, you can see that the toy might not work as well as I was showing in the picture at the beginning. So here is some literature on the VQE. These are some reviews that have appeared in the past, and some are quite recent. And then I will leave the floor to my colleague Walter, who will tell us what to do about these measurement issues in the VQE.
All right. Is it good? Okay. All right. So so I'll continue here in this session. Like Roberto nicely presented the VQE and this algorithm and some potential roadblock that this method could have. So one way to like overcome, for example, the measurement problem that we have. So like we have this operator in qubit space that is represented as a linear combination of Pauli strings. And so we have to measure all of them in computational basis and do this many, many times to get a reasonable error. So this is a very much an overhead in the measurement part. So there are techniques though to like lower this overhead. One way is, for example, doing implement this generalized measurement. They have some advantage. So how they work basically is that for each qubit we consider an auxiliary qubit, and we perform like two qubit transformation between these two, and then measure in the computational basis. And then what we will have basically it's like for all outcomes, for all combination of these two qubits, and we associate to this for outcomes basically an operator, a set of operator, and this operator are positive and semi-definitive operators that sum up to identity, and those basically they define what is called as a positive operator value measurement, and this is a generalized measurement because basically span the space of the operators in the Hilbert space, so we can represent each of the operators as a linear combination of this POVM. And so, and the nice thing is that basically the probability of getting an outcome will be basically just the trace of this operator. And so if we do it for each of the qubits that we have in the strings, so what we will have basically is that the probability of getting one of the outcomes will be like just the trace over this of this pi over the state of all qubits, and pi now will be like just a product of all the single qubit POVMs. Another thing that I already mentioned is that they are informationally complete because they span the space of operators, so we can like basically represent each operator that we want to consider as a linear combination of these POVMs, and then again when we take the expectation values of this operator, basically we'll end up having like a weighted sum over this probability of a given outcome. And this is very neat because, of course, we can use this for different operators that we are looking at. And for example, what we can do is basically like take as many shots as we need, and then like reconstructing like an estimate of our expectation value of operator that we are interested in, for example, the energy, and also the variance that we commit with, the variance of this measurement. One nice thing that we can do with this machinery is like optimize on the fly the measurement. And so how do we do that? Basically, once we get the we can parameterize the unitary between the ancillary qubit and the qubit that we are considering. And this basically, in the same fashion as the VQE, basically we will have like a parameterized circuit. And so we can do, after we measure we have an estimate of the expectation value of the operator and the variance, we can use basically classical post-processing basically to like calculate a gradient over these parameters to minimize the variance of the measurement over a given outcome. And so this will end up in like a better, or let's say, it will help us in finding a new sets of operators, a new sets of POVM that will be better in the next estimation. And so we can repeat this many times as up until we converge for a given error. And okay, we can, of course, we can repeat this process as many times. We do as many realization are possible, and then what we'll have is that we have an estimator of this operator and its variance as well. Now, so I said that this should save like resources, but as you see here, I've described the dilation POVM that consider an extra qubit for each one of the qubits that we want to measure. So it doesn't seem to be very efficient, but there are techniques like say that implemented the POVMs in a different ways. One way is that like consider this auxiliary qubit, but there are also techniques that takes into account the excited states of the Transman qubit that you are considering. This and then there are also implementation that they don't consider any auxiliary qubit, the so-called non-dilation POVMs. And then just to sum up, so this technique will allow us to, like, first of all, have a better estimation in the measurement at each iteration, and it scale up well with the number of qubits. And another very important feature is that we can estimate not only the energy. So if we optimize this set of measurement for the energy, usually for the Hamiltonian to find the ground state, but then we can use this to like calculate other observables or properties, like for example, reduced density matrices over this state, or commutators of the Hamiltonian with other observables like the number operators or the spin operators. And as well, we can use this extra, this generalized measurement to build up some noise mitigation technique that we can like apply after the measurement to reduce the error. And so now Anton will, after this, will explain how we use this machinery with the POVM to like consider a state preparation part that lower the measurement overhead for the VQE part. So I guess this is these are some reference. So we will see this during the demo. So I skipped a lot of details, so if you have questions, we can like maybe during the demo I can explain a little bit better. And then, next step will be state preparation techniques with this.
All right. So hello everyone. I'm Anton Nykänen, junior researcher at Algorithmica and doing a PhD at University of Helsinki on simulations of molecules on quantum computers. which is why we'll talk about state preparation. Yeah, so in a nutshell, the goal is to design a circuit, an ansatz, efficiently that spans the part of Hilbert space that has your target quantum state. And then you want to optimize the parameters of that circuit such that you find your target state, which is usually a ground state of some molecule. And while going on about this, there's a few things you want to consider. So first thing is again the expressibility. So you want your circuit to be expressible enough that it has target ground state, but you don't want it to be more expressible than that, because the larger your space is, the harder it is to find the one you want from it. And this will lead to problems in the optimization. Then you want your algorithm to be scalable, so it doesn't matter if it works with 10 qubits, it has to scale up to the relevant numbers you need for actual relevant simulations. Then you have the depth and the gate count. So with NISQ devices, near-term devices, you want to have the circuits as shallow as possible and as few gates as possible, so that the noise doesn't affect too much. Then we have the hardware layout. So if you have all-to-all connectivity, your qubits can each talk to each other. It's easy to transpile gates, but when you have limited connectivity, some gates are easier to transpile than others. And in the end, you have native gate sets. So usually you have rotations and CNOTs. But for example, if you, use Google's quantum computers, you might they have this native FSIM gate. So if you want to run on them, you could maybe use that FSIM gate. So a few things to have in mind. Then something about existing ansatz types and why something bad about them. So first is the hardware efficient ansatz. You have probably seen this. What's happening here? All right. Can I do anything about it? All right. Well, anyway, so you have your hardware efficient ansatz here. You have your rotations, and then you have your entangling layers of CNOTs, and then you repeat the structure n number of times, and you get your ansatz, which is expressible, and you can increase the expressibility by adding just more layers. But the problem is that it's too expressible. It has too many parameters, and optimizing it is a nightmare. And related phenomena is this barren plateaus. So if you think about your energy landscape, you start from a high point and try to go to ground state to low point. A barren plateau is a flat energy landscape where you cannot really sense the direction you should go. And even if you could, you would require very precise measurements to actually see the direction. And this happens when you have too many parameters in your ansatz. And hidden beneath here, it says break symmetries. So your spin and particle number symmetries are easily broken by these hardware efficient ansatz, which cause more problems in the optimization. And then we have the unitary coupled cluster singles and doubles, chemically inspired ansatz, as Roberto already showed. So it consists of fermionic single and double excitations. You can see them here, your single double excitation with fermionic annihilation and creation operators. So you form your ansatz by putting all the single double excitations there, and then you optimize the parameters. The problem is that will lead into very long circuits. You will have many parameters, and the gate ordering as this might not be optimal. So optimizing it is still not easy. And there are a bunch of improvements to this. It's very research area, but usually I think they lead to trades-off between, if you make it shorter, you will lose some accuracy. Yeah. So these problems inspire us to the adaptive ansatz. So the original adapt comes from words adaptive derivative assembled pseudo-Trotter ansatz, which has actually changed name a few times. At one point it was adaptive problem-tailored ansatz, and now I think it's adaptive derivative assembled problem-tailored ansatz. But in general, the idea is that you adaptively build an ansatz gate by gate. to match your problem, such that it is expressive enough that it has your ground state, but not anymore such that it's easily optimizable. So here's a flowchart I scavenged from the original ADAPT paper. You start by defining an operator pool, which here is your fermionic single and double excitations. Actually, these ones are even spin complemented, so you do the same number of alpha and beta electron excitations, so it conserves the symmetries quite nicely. So you have your operator pool. It's all the possible gates you can add to your ansatz. You start your ansatz from all 0 state. You apply few X gates to get your Hartree-Fock state, and then you enter this iterative loop, where in each iteration you add a new gate and then optimize the parameters. And you add the gate by their energy gradient, which is shown here. This is the gradient, and you can also see it in this form, where you have the commutator with the Hamiltonian and the generator of your operator, which is an observable, which is something you can measure on a quantum computer. So you measure all the gradients for all the operators in your operator pool, and then you pick the one that has the highest gradient. It will affect the state the most, and you apply it to your ansatz. You initialize it with parameter 0. The previous gates in your ansatz will keep their previous parameters. And then you enter your normal VQE routine and optimize all the parameters you have. And then you go on forward and at the next state, then next gate, until you have converged. And here the converge criteria is the total gradients in your operator pool. So when none of the operators in your pool have large gradients, that means you are probably close to an eigenstate, and you can stop. So in total, you will build an ansatz. It's shallow as possible. All the gates have a purpose there, and it's easily optimizable because each time you're adding only one gate, and that makes the optimization very easy, and it shouldn't get stuck in any local minimas. Yeah, then shortly about the gates you can have, the operator pools you can have in ADAPT. So the first set is your fermionic single double excitations. As you already saw, they are very chemically motivated, so the convergence is good. All the symmetries are quite intact. You can see them on the right here again. So you have your generator with a parameter which is exponentiated, and single and double excitations. These are in fermionic space, and if you want to implement on a qubit-based quantum computer, you need to map them. For example, with this Jordan-Wigner mapping. I don't know if you had anything about that, but when you take these into qubit space with Jordan-Wigner mapping, they look like this. So your single and double excitations, which have they have 2 and 4 XYs each term, and then these jet chains. The purpose of these jet chains is to enforce the fermionic anti-commutation relationships. And that's important here because if you move on to the next operator pool, this qubit excitation-based pool, what you do is you remove these jet chains, so you forget all about your anti-commutation relationships. What it does, it makes the gates more hardware efficient because you act on less gates, act on less qubits. It makes them more hardware efficient in all-to-all connectivity. It's not so clear on limited connectivity because if you have qubits far away, you still need to make them interact. And if you have the jet chain, it doesn't matter really if it's there. If you don't have the jet chain, you have to do swap gates to move the qubits next to each other. And that's why it's not that hardware efficient in limited connectivity. They claim, and it does have little effect on convergence on small molecules, but I don't think that's the case for larger molecules. At least in my simulations, I've seen that the bigger you go, the more effect you will get when you actually remove these jet chains. So consider keeping them there. Then last pool is the qubit adapt pool. So what you do is you take your fermionic single double excitations or your QAB operators and you split them. So for example, this double excitation has 8 terms in the generator. You can split it into 8 different operators here's the example of 2 of them. And it increases your pool size. And it will lead into circuits which are, they have more gates, more parameters, but they are more hardware efficient. And will lead to shallower circuits. The problem is that they do break symmetries more, so your particle number might jump away. So you need to keep that in check, maybe with penalties or some projections. Yeah. But in total, it should lead to the best convergence and shallowest circuits. Yeah. Then the next slide is for the non-believers of ADAPT. So the main claim against ADAPT is that the measurement overhead is too large. So each iteration you have to add a gate. You need to estimate all the gradients of all the operators in the operator pool, and that means lots of measurements on a quantum computer. They do have improvements on this, like grouping strategies and stuff, but the overhead is still there. Now, if you remember what Walt said about the ICPOMs, the IC is information complete. So with the same measurement data, you can estimate any observable. So what we do is, in an ADAPT iteration, we measure the energy, as we always want, and then we just use the same data to estimate all the gradients in the operator pool. And here's a figure showing results from simulations like that for N2 at equilibrium distance. There's a bit going on here, so I will just walk you through. So on the left figure, this dotted line here, it's an ADAPT VQE simulation with state vector simulations. And this line is where you aim to converge, this chemical precision line. The other lines, color lines, are simulations done with POVM measurements to different target precisions. So for example, this blue line here, you measure the energy till 8 millihartry error in the estimation. And you can see that when you measure close to 1.6 millihartry, which is the chemical precision you usually want to measure to, you will quite match the exact simulation. So without overhead, you can run ADAPT. On the middle figure, you can see different shots required for the different precisions, and on the right figure, you see different CNOT counts needed for different precisions. The dotted line, horizontal line, is again the CNOT count for an exact simulation. And you can see that you can match the same CNOT counts if you just measure the chemical precision. And a little overhead in the counts if you get a bit below it. Yeah, if you come to the evening, yes. I think this is STO3G. Because the point wasn't to like study the chemical side; it was just to. Yeah. There's actually I say chemical precision versus what's the other word? Chemical accuracy. So when I say chemical accuracy, I mean just what you meant, but precision, I mean the error compared to what would you get if you diagonalize the Hamiltonian. So what you can achieve with the current-based set. So yeah, it's not nowhere close to chemical accuracy, really.
We also have a question here from HackMD. I think it's a new question directed towards you. Why do you get psi HF using R gates? Can you elaborate on that?
You mean psi HF gate?
So why do you get psi HF Hartifock using R gates?
R gates. I said X gates. Few probably X gates.
Maybe the person can clarify the question in HackMD.
So your Hartree-Fock state is some ones and zeros and ones in your Slater determinant.
Okay.
Is that good?
Maybe there will be an update on the question. Let's see. And I invite anyone to ask further questions in HackMD.
Yeah. Yeah. If you come to the evening exercise session, you can try this out in the notebook. Then shortly about the selection criteria. So the default way is the gradient-based selection. It's robust, but not necessarily the most efficient. So here's an example of two different operators. The red it's an energy curve for different parameters for that specific operator. The red curve, you can see that the gradient at this point where it's measured at 0.00 parameter, the gradient is high, but it doesn't get below this. Instead, for the green one, which has 0 gradient, this parameter, it can get much more below than the red line. So it means that the low gradient doesn't actually mean that the effect on energy might be small. So instead, you can use an energy-based selection. So just pick the operator which lowers the energy the most. This is, of course, more computationally heavy. With state vector, no problem, but with measurements, the overhead increases. But we have also implemented this with POVMs, and you can also try that with the notebook in the evening session, afternoon session. And then there's also, you can use overlap to select your gates and optimize the parameters. So if you have your target state, or in a realistic setting, maybe an approximation of it, because you can't get the exact state, you can use that to calculate overlaps and pick operators that increase the overlap the most and optimize the parameters with overlap. But implementing this on a quantum computer is not that easy, calculating overlaps. It's state vector, it's all nice. And lastly, I have a list of references. So maybe to summarize, I believe AdaptVQ is a nice way to go forward. We have solved the main limitation, which was the measurement overhead. And yeah, next thing is maybe to think about the operator selection criteria, maybe make the criteria a bit more global information, because now Adapt is quite greedy algorithm. It has only local information each step. And then now, I think the bottleneck now is in the optimization of the parameters, so make that more efficient. That's all.
Excellent, thank you very much. Do we have questions from the audience or HackMD? Yes, please.
How are these IC POVMs related to classical shadows? Is there like some relation or?
Yeah, so classical shadows are like a subset of our POVMs. So the POVMs are parameterized, so with certain parameters they will match what classical shadows do. But we can optimize the parameters and find more efficient measurement effects.
Thank you.
And there's a bunch of further stuff we do with the IC POVMs that are not yet published, but there's stuff going on.
So a very simple question. Sorry, what's the question down? No. Do you know if there are similar adaptive techniques for QAOA?
I've seen, yeah. I haven't explored them myself.
Okay, but there is research.
I think you can make any circuit adaptive.
Yeah. Okay. Yeah.
You should do it.
Yeah. Thank you.
Thank you for a nice presentation. I am slightly worried about throwing out fermion statistics out of the door, just skipping the Jordan-Wigner Z-strings. So which systems would you actually go into problems just giving up Pauli principle?
Well, I think for up to 12 qubits or 14 qubits, the effect of throwing away the Z chains is small. But for 16 qubit problems, I've noticed the effect gets larger. So I agree with you. You shouldn't throw away the Z chains. Even in QAdapt, the regular way of QAdapt is that you take your QAB operators and split them. You have already thrown away the Z chains, but we have seen that if you actually have the Z chains in them, the convergence is much faster. Yeah, it's always a trade-off. The more hardware efficient you go, the less chemically inspired you are, and you try to find the balance between those.
All right, we are live again. Welcome back. I don't have anything much more to say except to introduce Björn Löfdahl here for a quantum finance use case.
Thank you very much. Can you hear me? Do we have audio? Perfect. So, hi, I'm Björn Löfdahl from SEB. First of all, I want to thank the organizers for inviting me to give this talk. And today I will present to you quantum support vector regression with a specific use case for disability insurance. And this is joint work with Professor Boelem Jihic from KTH. So during this talk, I will present an overview of a few different topics. And this will include disability insurance, kernels and support vector machines, a very short introduction to quantum computers, which you have already seen a lot of material on this workshop. And then we will talk about quantum kernel estimation. And then finally, we will be able to tie everything together into a disability model. So, health and disability insurance, it provides economic protection from illness or disability. So typically, an insured individual would receive a monthly payment from an insurance company in the case of illness. And for this, you pay, as an individual, a premium to a company. And this should cover the expected cost, more or less, of your potential future illness. So the insurance company needs to estimate this cost. And typically this is done by using some statistical models and looking at historical data. So they have a lot of data on existing customers and they want to find the correct price for a new customer. And the natural way to do this is to assume that you have some state space that your insured individual can move around in. It can be alive and it can be ill, and you can move between like healthy and ill, and you also have some dead state that we will all eventually end up in this state. This is the way of life. So we need to estimate the transition probabilities between these states, because the payments of the insurance contract depend on these transition probabilities. So, and one possible method for this is the support vector regression. So, to start here, we assume that we have some data, x and y, indexed by I. So it's a data set, and yi is some value that we can observe and want to build a model for. So in this case, it could be like a frequency of disability that we have observed for some subpopulation I. And xi would be some explanatory data that we can use to model y. And then we define a feature map, phi, which maps RD to some space f. It maps a sample data point x into a feature vector phi of x. So from a machine learning perspective, we take our data, we apply some function to it, and we have got a new feature. That is basically what we're talking about here. And this doesn't need to be in the same space. This can be in a higher dimensional or even infinite dimensional space in theory. But we need to assume that we have an inner product here, which we will denote like so. And then this feature map phi, it will give rise to something called a kernel through this relation. So if we have two data points here, x and z, then we map both of them into the feature space using the phi function, and we take the inner product. And this is the kernel between the data points x and z. And this is essentially describing a similarity measure between x and z, but not in the original data space. It's in the feature space. And the central set of functions here is the reproducing kernel Hilbert space, which is defined like so. It's the space of all functions, which can be expressed as an inner product between some weight w and phi of x. And this, if we think about this in, let's say, Rn, then this inner product between w and phi of x, this would be like w transpose phi of x, so that is some linear expression. So we think of this as linear models in the feature space, not in the data space, but in the feature space. So now we can introduce support vector regression. It is a convex optimization problem. We love convexity, don't we? And it has the following form. We are seeking to minimize some expression, and I would like to start describing it from this perspective here. This marked yellow part, this is our linear model in feature space. And we take it minus yi. So on the left-hand side here, we have the residual. And on the next line, we have minus the residual. So essentially what we're saying with these two equations is that our residual should be smaller than epsilon in the absolute value. And when it's not, we take some slack variable, which induces a cost to the cost function. And on top of this, we have a regularization term, which is this one, which ensures that we will have a regularized solution, which will hopefully improve performance out of sample. We will not have very high weights assigned to our features. So this problem is convex, and that is very good, but it can be very difficult to solve explicitly. But luckily, or rather, the whole reason why support vector machines are a feasible way of modeling is that we have the dual problem. So it's a standard case of an optimization problem where we have a primary and a dual. And the dual problem is looks a little bit strange. It's very difficult to recognize anything from the primal problem, but we have see that this kernel shows up in the dual problem. So in the dual problem, we are maximizing something which is a double sum over all our data, and the kernel between all data points arise in this expression. And then since we have a primal and a dual solution, of course, the solution or primal and dual problems, then of course the solution coincide. And it is given in the following form. So it is a weighted sum of kernels plus some intercept term, beta. So far I haven't said anything about what the feature map actually looks like. And this can be chosen in many different ways. But what we really want is we are seeking for something that is efficiently computable. So then we have a very tractable problem. So for example, well-known classical kernel, it is this Gaussian kernel, which has the following form. So that is one popular kernel to use. But what I will talk about is a more contemporary approach, which is provided by the class of quantum kernels. So in this case, what we do is that we take our data and we map it into quantum states using some quantum feature map. And then these resulting quantum kernels, they can be estimated on quantum computers. So I have here a brief introduction to quantum, but we have already seen this throughout the school. So I just remind of this representation of the state of 1 qubit in this case, which should follow this probability preserving constraint. So a quantum state, it induces a probability distribution on the integers 0 and 1. And at measurement of this state, then an outcome is determined, right? And in general, if we have 1 qubit, we can, as we have seen before during the school, we can represent it on the block sphere. So the state lives on the surface of this sphere, and we can we can manipulate the state by shifting the angles theta and phi here. And in this particular use case, what we will do is that we will take our data, the x's, right? And then we will make the shifts, the theta and phi shifts, be some function of the data. So we are encoding the data into quantum space in this way. So my personal view of how quantum can be interpreted. So I'm not a physicist. I come from probability and statistics. And I note the following, that programming a quantum computer, this is performed by you're writing your quantum circuit, right? And this circuit, it induces a probability measure on your bit strings or your binary numbers for a random variable, right? And whenever you are running your circuit, you will get an outcome on the bit strings. So this means that whenever you are running your circuit, you have a random variable and you are sampling from this random variable. So it is a probabilistic way of thinking about quantum computers and quantum circuits. Now, I think we are ready to move into quantum kernel estimation. So what we do is that as our feature map, we take, we call this a quantum feature map that we will take. It will map a data point into a quantum state, and we will do this by manipulating our angles on the block sphere, basically. So it's well known that any quantum state, it will satisfy the Schrödinger equation, which we have also seen previously during the school. So it has this form, right? And H here, this is the Hamiltonian operator for the system. And then we have the time-independent case, where the solution to the equation, it's just obtained by, you start with the base state that you have, and you add this linear operator to that, and you get your final state. And this linear operator is just defined as the matrix exponential, which depends on the Hamiltonian here. So then for every data pair, if we take a feature map and the data point x, then there is an operator which we call u phi of x that is determined by this equation. So we start at the ground state. So for a quantum computer, this is typically the 0, 0, 0, etc. state, right? And then we have some operator which we can define in terms of a circuit, right? So we add the number of gates, and then we arrive at some final state that we seek, right? And the kernel corresponding to phi. Now in this case, we will take this kernel here, which is, if we have two data points, x and z, we will map them to quantum states, phi x and phi z. We will take the inner product, and then we will take the absolute value squared. And there is a very specific reason that we will do this. So if we unbox this expression, it will take the following form. We will have the feature embedding circuit here that is acting on the ground state. And this is for the x data point. And then we have the adjoint circuit for the z data point. And if we take then all these two operators in the ground state together, then we can define this new state, phi of x of z, which is just defined by applying these two operators in sequence on the ground state, right? And then we can measure this state against the ground state, and then it turns out that the frequency that we observe, it will correspond exactly then to the probability, or that would be an estimator of the probability of measuring this state in the zero state. So, and this is what makes it possible to implement this then directly on the quantum computer. Yes.
Can I just bring up a question here from HackMD?
Yes.
So what is the advantage of a quantum kernel estimation compared to classical kernel?
So there can be a couple of different answers to this. So one possibility is whenever you have a kernel that you cannot calculate efficiently in the classical setting, you might be able to do it, or there might be kernels that you can evaluate efficiently in the quantum setting that you can't evaluate efficiently classically. That is one thing. And then I would say, I mean, in theory, we are mapping data points into features, right? That is the general machine learning principle. And if we can sort of extend the space of features that we can build by thinking also about quantum features, then it feels to me like we have a bigger space to work with. So in theory, we should be able to perhaps get better results for our machine learning models. But that remains to be proven. But that is the way I think about it, at least.
Is there any non-linearity hidden here? Is the feature map non-linear?
Yes, we can look at that because essentially, if we go back here, what we will try to do, I will show this later, we will try to encode the data into these angles here. So that will be some non-linearity in itself, right? More questions? No? Okay. So what we will do is that we will take the state psi of x and z, which we defined like so. We just apply the feature embedding circuit for x and the adjoint circuit for z onto the ground state. We implement this into a quantum circuit. We run this circuit n times, so then we are sampling from our random variable. And k of z, this is just estimated to be the frequency of ground state measurements. So then it is exactly this form of kernel that we take the absolute value squared that enables us to measure it directly on a quantum computer. Yes. Now, so we can consider a population of insured individuals. And we have this variable EI here. This would be the number of healthy individuals from the population subgroup I. And we have DI. This is the number of individuals that are falling ill among EI. So if we take D divided by E, that would be some rough estimate of the frequency of disability, right? And then for each subgroup I, there is some associated data that we have, the XI, and this may contain, this contains some information about the insured individuals, right? So they have told the insurance company, this is the data that describes me as an individual. So, for example, I will show an example where we have age and gender as our two variables. And then we define also P of xi. That would be the probability that if you take an individual among the EI, then that would be the probability that that individual falls ill, right? And this would depend on the data xi. So then we propose a model like so. We take the logistic transform of the probability. So this is defined as log p divided by 1 minus p. And we assume that it has exactly this form. So this is the form for the solution to the support vector regression problem. So it is a weighted sum over kernels and an intercept term. And here we are yet to specify our quantum kernel. Okay. So the plan is to do the following. We define a kernel by creating a quantum circuit that encodes our data into quantum space. And then we estimate the kernel matrix. Then we can solve the optimization problem. And that will give us the parameters alpha and beta. That is the plan here. And the reason that we are doing this particular transform, it is because then we can guarantee that the resulting probabilities, they are in fact probabilities. They should lie between 0 and 1. So it's just a function that maps to this interval. And our data has the following form. We have xi, 1. This is gender. And then we have age, or a normalized age rather, which we have in the xi, 2 variables. We have two-dimensional data here. And then we have defined this feature embedding circuit, which looks a bit daunting, and I will not try to explain it from this perspective, but rather we will look at it from its graphical representation, namely the quantum circuit directly. So in this case, we have 2 qubits. You could, of course, define any number of qubits and do any number of operations, but in this example, we have restricted it to 2 qubits. And then we have a couple of operations here. So we start by applying an RY gate, which rotates by pi times xi, 1, and xi, 1, this is the gender variable, so it can take the values 1 or 0, right? So then, if you think about what happens from this gate, we start in the 0 mode, and then, or in the 0 state, and then potentially we can flip it to the 1 state, right? So all the populations that are in one gender group, they will be in this state for the first qubit, and for the other group it will be in this state for that qubit. So we are, with respect to only that qubit, creating like a maximum distance between the two genders, so to speak. So we're saying that they are dissimilar. And then the second variable, this is the age, and we encode that into the second qubit. So let's say that we have some normalized age here. So we take the age, we multiply it by pi, and that will give us some rotation on the Bloch sphere, right? And if we have 2 population groups with like almost the same age, then the angle between those will be small. And if there is a big age difference, then the difference in angle will also be big. So the bigger the age difference, the bigger the difference in this feature space, right? So the idea here is to just create this measure that would bring a I mean, we are trying to create a similarity measure here, right? So this should feel intuitive. We're trying to clearly separate the two genders and cause this gradual increase in age groups, right? So what do we need to do? Oh, yes.
Maybe I can just interrupt with
Yes.
another question from our online audience. So, coming back to what you said before, do I understand correctly that once you computed machine learning model on a quantum computer, you can use the model on a classical computer to estimate the probability, but how demanding is training the quantum ML model?
So in this case, we have a rather simple circuit that we have implemented. So running this circuit like once is almost trivial, right? But on the other hand, you need to run it once for each data pair. So then it grows quadratically with the number of data points that you have. Was there another first question? Or? Okay, I hope I answered it. So remember, we need to implement this state psi, right? Which is defined by adding the feature embedding circuit once for x and then running it on reverse for the set data point. And this looks like this if we look at the circuit diagram. So we start in the ground state over here. And then we add the circuit for xi. And then we run the circuit in reverse with a change of sign on the rotations for xj. So to give some intuition on this, let's say xi and xj are the same. What happens then? So if we start from the middle, here we have some rotation pi xi, and we have the same ry rotation minus pi xj. So if xi and xj are the same, these two blocks will cancel. Okay, so we can remove them. And then we come to the middle here, and we again have rotation pi xi, 2 and minus pi xj, 2. So they will cancel. And then we are left with this one, which will offset this one. So they will cancel, and this one will offset this one. So if xi and xj are the same, then all these boxes will disappear, the circuit will be trivial. We will measure always the 0,0 state. And this is good because we want this to be a similarity measure. So if the data is the same, then we get the value 1, which is the maximum similarity, right? And if the data is not the same, then the probability of measuring the 0,0 state will decrease, so it will be lower. We will always see some other states showing up, right, in our measurements. So for these two terms, you mean? Okay, so for this case, we wanted to add some sort of interaction effect. So what we do here, we do some rotation in around the z-axis with respect to h, but we only do this for one of the genders, right? Because the first qubit will be either in 0 or 1. So for one of the genders, we will do this additional rotation, and for the other, we will not. So that means that, well, the idea is that you can have like different age effects for the two genders, for example. So it's that sort of interactions that we do.
And the age group, is it discrete?
Yes, it's a discrete variable. So typically you would take the age directly and normalize it, or you would take age groups like age 40 to 45 and 46 to 50, etc. Yes, so for the quantum part of the experiment, we ran this on Yorktown, which is now a discontinued machine. So for each pair of data, xi, xj, we ran the circuit 8,000 times to estimate the kernel. So remember, since we are sampling, we're running the circuits, we're sampling from a random variable. So we have some sampling error, right? The circuit that we are, I mean, we can think about this. Do we measure the ground state or don't we measure the ground state? So that is like a 0-1 random variable that we are looking for, right? So we have a Bernoulli sampling error in that case. But with this number of draws, this sampling error is always smaller than 1% in absolute terms, which means that for this use case, the hardware error will dominate actually. So we will run this on the Yorktown, and we will compare it with a result from a state vector simulation. So the estimated kernel matrix, it looks like this. So it has a very interesting structure with these blocks. So if we think of this as the first, second, third, and fourth quadrants, then here in the second quadrant, we have all the groups that correspond to one of the genders. And what we see is that so the darker it is, the darker the color of the blue, the higher is the similarity. And in particular, on the diagonal of this matrix, we should always have ones, right? Because similarity between xi and itself is 1. And then what happens is that when we move away from the diagonal, what we actually do is that we increase the age difference between two age groups, right? So if we would look at this specific cell in the matrix, this would be the similarity between group 0 and group 30 or something. And that would correspond to an age difference of something, and that would cause this kernel value to be lower than 1. It would be something like 50% or something. So the further you move away from the diagonal, the higher your age difference becomes, and the lighter the color of the blue becomes. And the second, the other gender group is located here, and we have a similar structure. And then for the first and third quadrants, the kernel is has very low numbers, right? It's almost 0, and this is intuitively explained that we had this like 0-1 shift in the first qubit depending on the gender. So the similarity between the genders here is very low. Intragender, it is high and depends only on age. And we run the same simulation on the Yorktown, and we get exactly the same structure of the matrix. However, the actual values that we observe are a little bit different if we switch back and forth like so. And in particular, it turns, I mean, it seems like we are always measuring a much lower degree of similarity. And this is due to these hardware problems. But the structure is the same. We have higher similarity closer to the diagonal, and the further we move away, the lower the similarity becomes. To be concrete here, we started with the data. These are our blue and red dots, right? So we have on the x-axis we have the age of the population group, and we have the two genders. We have females and males in this case. So they're represented by red and blue dots, respectively. And then we have on the y-axis we have the inception probability, and this is now hidden in this graph because it is like company secret data, but it doesn't matter. This is like a few percentage points, right? And then we have a couple of lines here. So the dashed lines they correspond to the state vector simulation, right? And the fully drawn lines, they correspond to the model derived from the Yorktown kernel. And interestingly, we see that the model results, they are very, very similar between the theoretically true model, so to speak, the state vector simulation, and the simulation that was done on a quantum device. So I think that is an interesting result in itself, that even though we saw that the numerical measurements were rather different in the two cases, the structure that we saw in this matrix was still retained, and probably that is what gave us these very similar modeling results. So if we do leave one out, cross-validation on this data, it still turns out that the classical model was the best. So a polynomial kernel of rank 2, I believe, turned out to be the best one in this case, with the state vector quantum kernel just lagging a little bit behind. The difference is very small. To me, this is, I mean, more or less the same accuracy. This is just like measurement error in some sense. And the actual result from Yorktown was, again, slightly worse than the state vector version. So, to conclude, we have proposed a hybrid classical quantum approach to estimate disability inception probabilities. And we've seen that performance is very similar to classical models. But I want to point out here that this approach is by no means restricted to insurance applications. So, for example, I work in a bank, and we are very interested in credit risk, in fraud detection, that sort of problems. You can use it to separate cats from dogs, or whatever you want to do. You know, these classical problems. And I think that as hardware improves and becomes more powerful, there is a chance that this approach can outperform classical models, but it remains yet to be proven. And to finish off, I have a list of references here, and I will recommend this reference for the interested reader. This is an excellent introduction to quantum kernel estimation. So with that, thank you very much for your attention.
We have a question.
Hi, my name is Ebba. I'm from Swedish in Karolinska Institutet. Thank you very much for a great presentation. Could you say something about what, for example, Goldman Sachs and HSBC and JP Morgan are doing on quantum? Or how they are investing?
You mean quantum in general? Or I don't know exactly how they are investing, but I do know that JP Morgan researchers have published several papers on, or quite a few papers on applying quantum methods in finance, and that I mean one example would be for the asset pricing problem, where they are proposing to use quantum Monte Carlo.
Any further questions? Yes.
Yeah, maybe it's a trivial question, but it seems to me that the way you design the future map and therefore the kernel is a bit of a heuristic. Like, is there any way you could go about designing that, like for other applications? Like how would you go about it?
Yes, so I have chosen the approach that I try to create a feature map that is intuitive to the problem. But you could also take like just a data-driven approach. You could just use a big number of different rotations and control this with some parameters. I mean, that would be some hyperparameter of the problem, and you could then do like iterative estimation and improvement of this hyperparameter. So then you could sort of fit the kernel to fit your data as good as possible in some sense. So that is also a possibility.
Yeah, thank you.
Further questions?
So, person, if I understood correct, there was no quantum advantage in this case?
No.
Right, yeah.
No.
Whether this normalization affects the result, because choosing the normalization method can probably give different results.
Yes, that is a very good question. If we go back to the block sphere, then in particular what we say is that we encode the data into these angles, right? So if we would start moving, I mean, into the like opposite side, onto the sort of backside of the block sphere, maybe that wouldn't make so much sense. It makes more sense to just restrict it to one of the sides, right?
Let's take 2 questions for our online audience. So how were the subgroups defined?
So in this example, we had 2 variables, right? We had the gender, so that was the first split. And then we had the age. And then in this case, we just split it into one group for each year, I believe. And that gave us about slightly above 80 groups in total.
And one more. What's the difference between state vector, parentheses, quantum kernel, and Yorktown kernel?
So the state vector simulation, that is when you are running a quantum simulator and you get the result explicitly by getting the final state as a result. So you're not using this sampling technique, right? You get the state explicitly, and then from the state it is so that is like deterministic. So then you get an exact estimate of your probability of measuring the ground state. Whereas for the Yorktown kernel, we sent this information that was needed to calculate the kernels through the IBM cloud onto the Yorktown machine, and it sampled these results for us. So we get an estimate from an actual quantum computer, which is what we see in this slide.
Right, welcome back. So it's our pleasure to introduce now Ebba Carbonnier, and followed by Hanna Linn for a quantum life science use case.
Thank you very much, and thank you so much, Tor and everyone, for having us and having the interest in quantum life science. I work as a director for our newly established Quantum Life Science Center. It's a national center at Karolinska Institutet, and I'm also a portfolio manager at Swedish, where I work with large national projects on gene sequencing and cell and gene therapy and biobanking, etc. for Sweden. So regarding our Swedish Quantum Life Science Center, you can see the partners that we have here. And today I will introduce quantum life science to you, and then Hanna will take you through an example regarding protein folding. So we will briefly discuss why quantum life science, and then where are we doing it here in Sweden and also in the Nordics and in the world. and some of the examples that we are working on. So why are we doing this in Sweden? We are a stronghold for quantum technology, and we are strong within health and life sciences. So, as an example, US, of course, US is not everything, but US has selected 11 countries for collaboration within quantum technology. And Sweden and Finland and Denmark are 3 out of those 11 countries. So that could say a little bit of the situation within the countries and how far we've come within quantum technologies. And in general, we are strong as well within health and life sciences, both in Sweden and the Nordics. And also, if we go down into the very, very fundamental parts of this, that personally, I am very intrigued by this, that if quantum mechanics is the operating system of nature, we, within health and life sciences, have a lot to learn here. So the fundamental effects, but of course, applying the quantum technologies to have health and precision medicine within health and life science. So this is highly relevant, of course, on the quantum effects and the fundamental parts in understanding our molecular biological processes. And this I've mentioned, that the strength in quantum technology and the strength in health and life sciences, and this gives a competitive edge. So what is happening within quantum life science in Sweden, the Nordics, and worldwide? We started in 2018, and I will come to some short facts here regarding what we are and what we do. And perhaps you know also about Denmark and the Novo Nordisk Foundation, that they are investing 1.4 billion Danish crowns from the Novo Nordisk Foundation for building the hardware, but then it is actually developing life science applications. So in the Danish state, they are also investing now a billion Danish crowns for a 4-year period, and most likely another billion Danish crowns for the next coming years. And then we're of course very happy in the Nordics here that we have Algorithmic that is working hard on the quantum chemistry, which is of course in the life science, bringing quantum to life. And we have our friends Norway here as well, with working, starting on the life science. So this results in that we started a Quantum Life Science Roundtable, a Nordic Quantum Life Science Roundtable in 2021, which we have now recurring within the countries. So we had it in Sweden in 2021. In 2022, we had it at the Novo Nordisk Foundation. And this year, we will have it in Finland. And there is also a Centrum for Quantum Biology in Germany. And in UK, there is a Quantum Biology Doctoral Training Center. And then in the US, of course, there are groups here and there, but the big investment and where things are happening, we were just over there in September, and most likely it looks like we will collaborate with Cleveland Clinic. Maybe you have heard that they are collaborating with IBM, and it's one of the first installment of a quantum computer in a private setting. So they have a quantum computer at Cleveland Clinic. And Cleveland Clinic and Mayo Clinic are actually the ones competing for the best hospitals in the world. So this is quite a good combination. In Sweden, we have Karolinska Institute, where I'm at, and Karolinska University Hospital, which we're number 6 in the world. And then there is an Institute for Quantum Life Science in Japan as well, and a newly started in Australia, a Quantum Life Science Center. So there are things happening, but as it looks right now, we were quite early in the Nordics. And as I mentioned, we started off probing what can we do within the quantum sensing side, the quantum computing side. In 2018, in close collaboration with WACQT. And then we started off this our Quantum Life Science Center and the Nordic Quantum Life Science Roundtable here, because there is such an interest in this area within the Nordics. And some fast facts, if we dive down now to Sweden. Yeah, okay. So some fast facts, we have 8 projects, so both within computing and sensing. And then we have also this pre-study of Cleveland Clinic, where we will collaborate with them regarding both the computing and sensing. And it's within the DNA and omics side and the protein folding, which Hanna will dive into. And there will be a hands-on session as well. And then it is, and that, for example, on the protein folding, it can be very useful because, for example, with Parkinson and Alzheimer's, etc., we have to learn more about these diseases. And on the spectroscopy, microscopy side, there are, we hope that we will understand more, or rather, they are earlier because it's on the sensing side. They're already operating in the clinic. Operational in the clinic. It's actually about high resolution in the brain with magnetoencephalography and optically pumped magnetometers to have high resolution in the brain. And this is, for example, with epilepsy. It's very of great value. And then we have the spectroscopy for understanding for example, breast cancer tumors with higher resolution on the breast cancer tumors, and to see the tissue oxygenation in the heart, for example. So those are some areas that we are exploring. And it is early stage, but it seems that Cleveland Clinic, a little bit in Denmark, and here in Sweden, and of course in Finland, there is great work being done as well. It doesn't seem that there are other areas or countries that have come further of what we know. So please tell me if there is work that you know of in quantum life science in other countries that we haven't discovered yet. So we have these 8 projects. We have 5 companies, 4 startups, and of course AstraZeneca, a large company. And we're 25 people, and we have this management team. So these are the 8 projects, and this was just a brief introduction. You're most welcome to talk to me if you want to know more. And thank you from the Quantum Life Science Center. And also, we have done a Swedish quantum agenda, because of course we hope that if we step up a little bit now it's not just quantum life science. The quantum agenda is about quantum life science, quantum energy, quantum defense, quantum security, quantum finance. We need to get our Swedish government to invest around 5 to 8 billion Swedish crowns during a 10-year period, because then we would be in comparison doing well in comparison to other countries. Because I don't know if you know about Finland just did a great investment. It was known yesterday. And of course, Denmark are investing greatly, and many other countries, for example, UK are investing 32 billion Swedish crowns, and Germany are investing 64 billion Swedish crowns, etc., etc. So that is why we have done this Swedish quantum agenda. And there is more information regarding what's done on the research side, what's done on the company side, on the commercialization part. That was all for me. Thank you.
There are some questions directly at this stage.
So, let's go. And I'm supposed to point on here. Yes. Hello, my name is Hanna. And I'm a PhD student at Chalmers together with WACQT. I have my supervisor, Göran Johansson, and my co-supervisor, Laura Garcia Alvarez, working with me on how to apply quantum algorithms within life sciences. We started out with metagenomics, but then we transitioned into protein folding. And this is what I've been working on for the last almost 3 years. So, an overview from today. I will talk about like what is protein folding, what is just the biology of it. And if we would want to do the protein folding on a gate-based quantum computer, specifically using QAOA, that I understand that you already heard about earlier in this autumn school, and how we can be inspired by other quantum algorithms like quantum annealing in order to maybe make QAOA better. But then the big questions that I've been working on mostly is what kind of quantum computers would we need in order to challenge classical computers in protein foldings? So, to start off with protein folding, we start in the top. This is going to be tricky here. So, we start with DNA. DNA is read into messenger RNA, and then it's translated into amino acid sequence. And this is the first stage of protein folding. The first fold is just putting together the bead chain. Going from a bead chain to a functioning protein, this is the hard part. And if we would want to simulate this to understand how it works in the body, we could either take the fully atomistic hundreds and thousands of atoms and try to simulate the molecular dynamics of it, or we can do some coarse graining where we take away a bunch of the details and just say, okay, if we just divide all the atoms firstly into big beads, one bead for each amino acids, and then we can do even more coarse graining of saying, okay, one bead can either be hydrophilic or hydrophobic. So we also take away all the differences between the amino acids. Well, all the ones except one, if they're soluble in water or if they're not soluble in water. And then we put them on a lattice. So we don't even do it in a 3D all continuous space. We just say it can be on a square or a cubic lattice. So qubit would be in 3D, but the angles are set. And still, this is an NP hard problem to find the best fold from just the amino acid change. So it grows exponentially. So we do the coarse graining for simplification, and I work with different models trying to say, okay, which one would be able to be run on a quantum computer. But today I'm going to focus on the hydrophobic polar model, so what's called the HP lattice model that you see here. We have a small folding. So the question then is, if we would want to do the simulations classically, which is usually do with a random walk or some kind of Monte Carlo algorithm, and then if you want to do it with QAOA with quantum instead. So, a big reminder of what QAOA is. We have our circuit that's in the quantum computer with different layers of the cost and the cost Hamiltonian and the mixture Hamiltonian. The cost Hamiltonian encoding the information of the protein. So the cost Hamiltonian is going to be dependent on the protein, and the mixture Hamiltonian for mixing it up, and the cost Hamiltonian for like honing it down. And we have the classical computer to optimize the parameters, so updating gamma beta. And we have different layers of doing the same thing over and over again. So all the math goes like this. And what we want to do in the end is get the best solution. It's very confusing seeing in two places. Best solutions in the end with the lowest cost. So the folding that has the lowest energy. So this is the wonderful thing that we want to see. So in the training, we want to see that in the number of steps going downwards, we're optimizing gamma beta, doing this loop over and over again. We start with the initial parameter, and it wonderfully goes down here. Hopefully. Usually it doesn't do this. Usually we don't have this nice spike of the super, super nice one, because the energy landscapes doesn't look too well. So the two questions becomes where to start, and if we could take inspiration from another quantum algorithm, and further, how large would this quantum computer be? How many qubits? How many gates do we need? And what kind of connectivity would it need? So the energy landscape looks like this. And this is also with some after processing of making it nicer. We want to find the best parameter, which we can do a very rigorous search. We can check for each and every combination of gamma and beta, and we can find it. But how do we make sure that we start in the right place so that we can walk to that part? And this is for p equals to 1, so if we only do one layer of it. So we start with the initial parameters with what's called a warm start, invented by WACQT et al., where they use inspiration from the annealing algorithm. Have you heard earlier about the annealing algorithm? Can we get some thumbs up or down? Some people have, some people don't. So this is what's used in the D wave, where it's a fully adiabatic transition between the cost Hamiltonian, the mixture Hamiltonian to the cost Hamiltonian. So we have this like gradual steps going downwards. What's the difference between the QAOA is that we have a trotterization of the energy going downwards. But we can still take inspirations and say, okay, but if we do it step by step, if we go slowly, shouldn't we then get something good? And we can see that the success probability of getting something out, it's not too bad. In the very, very small lattice case, the smaller the lattice, the easier to fold, because there's not too many things to look for. We can get the success probability of 90%. It's like, yeah, 90% success probability. If you're in machine learning, that's quite well. Yes, but this is taking 4 amino acids and placing them on a grid that only have 4 spaces. So you can do it by hand or just by not looking at it. And then in the same of here, just with like the toy problems of a very, very small lattice size of 3 times 2, we get the success probability of 50%. Oh, that's not too good either. And then with the 3 by 3, now it's a tiny bit harder to put 4 spots in 9 places. It's still, maybe we can find something better. Can you explain the graphs? Yeah. And then radiance. So radiance is, I can repeat the question maybe. So the question was, explain the graphs. That's a good idea. So what's on the y-axis is radiance. So that's the gamma beta parameters. So for example, if we say gamma beta, so we have, let's see. We have the two gamma and beta. Gamma is always going to be a circle, beta is going to be a square, and then on the x-axis we have p. So at what part of the algorithm is this going to be what part? So when we start off, the first p, we see that we have a low gamma and a very negative beta, and then they slowly go upwards. So you could also say that we're turning on beta. No, we're turning on beta and we're turning off gamma. So we're turning off the mixture Hamiltonian and we're turning on the cost Hamiltonian, slowly, one step at a time. You could do this with a linear function, which is the straight lines, or you could do this with a cosine function. Did this explain it? Yes. Sorry. One more question. I think it skips. So I'm just going to make sure that it pauses, but it keeps jumping forward when I don't want it to. Okay, now pause it.
So you're doing this on a 2-dimensional lattice or 3-dimensional?
This is a 2-dimensional lattice.
As a toy problem, or?
Because
it's a toy problem? Or
because it's a toy problem, yes.
Otherwise you would be doing it in 3 dimensions?
Yes, but then also it becomes kind of a toy problem. If we want to make it like to not being a toy problem, we have to do more than 4 amino acids. We have to do like 6 amino acids, and then the number of qubits explode, which we will see soonly. And even then, it's a very heavily coarse-grained model, so you would have to put even more details into it, and then it becomes an even harder problem. But what we can see from this is if we take the initial parameter from the quantum annealing and then we train it, because what we can do with the QAOA that we cannot do with the quantum annealing is doing the training part. So we say, okay, you got it this good, can we optimize it? And then maybe say, oh, but it's maybe linear wasn't too good. Maybe we should have started with something like tangent or a cosine or something like that. So it gives suggestions of how maybe we could improve it, to taking a step further. Sometimes it finds the same minima, but we can see that we have gotten some improvement for the 3x2 lattice, for example. But there is improvement that's maybe not too big. Maybe we can get a better improvement if we do scale up the system, if we make it to a larger lattice or with more amino acids. Here comes the limits of the sizes of systems that you can simulate for a quantum computer, because this is 18 qubits, and with the number of gates that this takes to do with 10 layers of the QAOA algorithm, it's hard to simulate something bigger, and this is the point where we maybe need a real quantum computer to run it on. So here you see the on the x-axis we see the number of qubits, and the number of qubits is correlated with the size of the lattice. So here's a 2x2 lattice, here's a 3x2 lattice, and here's a 3x3 lattice. And we see that the success probability, so the probability of finding the best state, goes down with the size of the system. But it's because the optimization becomes harder. So this is doing the same optimization for all of them. Of course, if you have a bigger system, you would need more optimization. And this is with a very naive, just Adam optimizer thrown at it. But what's the point with this is, like, we get better by doing the training. So the darker ones are for training, and we see that for both the linear function and the cosine function, it does better. And for the just setting random initial parameters, it makes a lot better, of course. So, the second question. From current proof of principle that we see so far, if we would want to do practical implementations, how big would the computer have to be? So I've looked at resources, the number of qubits, the connectivity of the qubits, like how many qubits in each gate, and then the number of gates this would need to be encoded. And we looked at 3 different protein models. First, the sidechain conformation-based model, which is a less coarse-grained model, where you say, okay, we have a carbon backbone, and we just want to switch the side chains around. And then we have 2 HP lattice models, where you either focus on the turn-based one, okay, I'm here, which is the next turn, I'm going to place the next amino acid, or the coordinate-based one, where you say, okay, we're encoding which coordinate each amino acid is on. And then we look at different bit strings encoding, so either the one-hot encoding, where we turn on one bit at a time, the binary encoding, which is more dense, that uses the binary numbers, or a combination of the two, which is called bit unary binary. So we have unary in the sense of which block is turned on, but we have binary in each block. And here we have an optimization parameter called G. For the remainder, I'm just going to put this to 3, because G is just going to make BU binary go towards one-hot encoding or the binary encoding. So if we specifically look at the sidechain conformation-based model, which you see here, we have a backbone, which is the spirals, and then we just want to optimize for the side chains. And then the coordinate-based model, which is this one here, where we focused on which coordinate has each amino acid gone to. On the x-axis, we have the number of amino acid, so the measurement of like how big a protein is. And the average size of a human protein is about 100 amino acids, or a few hundred. A hemoglobin, which we have a lot of in our blood, is 200 amino acids. So this is like kind of the size that we would want to go to. And then on the y-axis, we have the number of qubits, the number of interactions. So interactions not taking in how many qubits, as you're saying, how many terms in the Hamiltonians, basically. And then if we do a decomposition into 2-qubit gates, which is mostly what we're able to do today in superconducting hardware. And we can see that the number of qubits is maybe not too far. If you look at what IBM has published lately in saying, okay, we will get to 1,000 qubits quite soon. If you use the binary encoding, it works out fine. It's below 1,000 for the sidechain conformation-based model, and also for the coordinate-based lattice model. It's not too far. It's 6,000 for the largest ones. What is the limiting factor, as you may see, is the number of gates we have to do. 10 to the power 8. That's a lot of gates, I can tell you. Right now, we have a fidelity, or like in current state of modern quantum computing hardware, we have a gate fidelity of 99.9. I'm saying it rightly. Yes, I got some, yes. So if we want to do 10 to the power 8, we're just going to get noise in the end. We have to get way better gates before we're even able to do one set of the cost Hamiltonian. So only p equals to 1, we will get noise if we want this big things. So before we can run even the coarse-grained models on a quantum computer, we would need larger gates. But I would say it's positive that we have enough qubits, so that's good. We can start there, and maybe then from this you can draw the conclusion that maybe we need models that uses less gates. A way of simplifying it even more, or using some smart geometries to rinse through it. And we can also see that the binary encoding is using less qubits, but uses way more gates. The one-hot encoding is the opposite. It uses way more qubits, but way less gates. And the BU binary encoding is in between. And with the G parameter, you can even shift it to one or the other. So if we have a hardware that's maybe has an easier time doing a lot of gates, but has fewer qubits, like an ion trap, then we would want to use the binary encoding. But if we have a superconducting hardware that has a easier time doing gates, but only 2-qubit gates, then and has more qubits, then we would want to use the one-hot encoding. And we can use the BU binary encoding to accommodate if we have another set of native gates or so on. So in summary, where to start? Well, it's not a bad idea to start with the annealing parameters. How large would it be? Well, very large, or very deep. And that's my ending. Do we have any questions? Yes.
The first question is, when you write a Hamiltonian, so it describes which level of the protein?
Describes
which level of the protein? We have 4 levels: primary, secondary. So which level the Hamiltonian you are describing?
This is second level.
Second level.
Yes.
So now, when we're talking about protein folding, compared to the Google AlphaFold and all the traditional methods, what will be the relatively strength or weakness when we're doing this in quantum? And with the hope that you can have some promising hardware in the near future.
Yeah. So partly why you would want to do coarse graining is a part of or coarse graining models from the start is part of a bigger pipeline. So if we in the end we want a fully atomistic model of what we did in the end, then maybe we start off with a coarse grain model to say, okay, this would be the backbone, and then we can do the sidechain optimization to say, okay, this is the initial guess, and then we can put it into a molecular dynamics simulator to get all the specifics of it. The question was more like how. Yeah, the relative in strength.
Because since AlphaGo already do so much, so
Yeah.
if you want to invest this new method, especially in quantum computing, at least we need to know that why this thing we need is better or worth using, right?
Yeah. So I would say AlphaFold does a different thing. This is why I have the slide. It answers a different question. So for protein folding, we have 3 questions. We have partly what energies goes into it, what parts of like molecular dynamics actually go into it, and how can we then build up a energy function. The second part is the folding mechanism, like how does the energy landscape looks like, how does it like fall down into the right native fold. And lastly is based on the amino acid sequence, can we predict the structure? And I would say AlphaFold solves the third question. It doesn't make the other 2 questions not interesting. So I still think that quantum computing would help with the 2 other ones, but especially answering part 3 if it doesn't use stuff that's in the training data set. So AlphaFold is trained on the protein data bank, which is you take all the synthesized proteins that we have, and then you take a picture of them in with the crystal that thing, you freeze it down and then you take a picture. Yeah, it's hard to say. But it's only for the 20 canonical amino acids. So if you would want to go outside the realm of canonical amino acids, which maybe would want to do in drug design, you would want to put something else in there that's not naturally in the body, to change something in the body, then we would need other ways of doing the same thing as AlphaFold is doing it, but without having the dependency of always having this training data set. So I would say it has a partly in the pipeline, because also AlphaFold is like, it's not one button, it's a lot of things going in between. I would say that's maybe parts of it we could do with a quantum computer. But as I said, it's long in the future and we need better hardware and better models in order to do this. Yep.
Thank you for the great presentation. I think you mentioned that this was purely done on gate-based quantum computers.
Yes.
Have you looked at using like D-Wave quantum annealer?
We haven't, but we have a collaboration with a group in Lund that does the exact same model on the D-Wave. It's gone pretty good for them, I would say. Yeah. I think their biggest conclusion is they can outperform classical computers, not running it on the actual CPU. Should I get it for you? Sorry. Not running it on the actual CPU, but running it on the hybrid. So there's something that D-Wave does that breaks down the problem, that makes it like so you actually get a better solution. D-Wave have thousands of qubits, so they've been able to run amino acid sequences up to 60 amino acids. And in the pure QPU, it doesn't work too well. It makes noise. But in the hybrid version, it and especially in the simulation part, it does better than classical algorithms. So somehow in translating it into a QAOA model and then giving it to D-Wave, it's better.
Yeah. You know if they have published anything?
Yes, they have one publication and one on the go.
Okay.
I can maybe give it to you
sure.
somehow.
Thank you.
By Ebba et al. And they published it last year.
Thank you for a very nice introduction to this. I would like to understand a little bit better the scaling of the gate depth. But
okay.
I think to begin with, maybe how is the cost function that you're actually simulating? So you're placing a string of hydrophobic and hydrophilic beads on a lattice.
Yes.
So do you have only on-site exclusion or also nearest neighbor hydrophilic, hydrophobic interactions or even more long range?
No, we only have nearest neighbor.
Okay.
Yes.
Thank you.
So it's not the IBM where you can take even a step further. But we have compared with the IBM one, and it scales about the same. Yes.
So this was folding in like isolation in free space.
Yes.
How far are we from modeling conformational changes, enzymes, cofactors?
On a quantum computer, very far. On classical, I am not the right person to answer this, I would say.
Okay, so no dynamics yet then?
No dynamics yet, I would say. The hardest model that I've seen is the sidechain backbone fixed problem. And there, of course, you could, like in the big energy function, I have an example of it here. In the big energy function, so this is the rotamer model, so rotations of the sidechain. And here we say, give an interaction of 2. Oh, this is a very bad color on the... I see now. We have the two-body interactions and the one-body interactions. And of course, in the two-body interaction, which is a summation of van der Waals interactions, electrostatic, being in the same place and so on, we can put more. We could maybe add water into it. But it's statistically based, so... Yep.
Any further questions?
So what we're going to do in the afternoon is starting from quantum annealing parameters and seeing if we can get a nice graph out like this. This is a spoiler.
Hello? Yes. Yeah. Okay, welcome back, everyone. I will steal a few minutes now at the beginning of this section before I hand over the word to our tutorial masters. So I will start by handing out some acknowledgements. And where is that? I just want to acknowledge, well, let's start here. Instructors and helpers, because I expect maybe some of you to be leaving at some point, maybe not, maybe before we round off the day at 4 o'clock. So before you leave, I want to hand out thank yous and acknowledgements to all the people that contributed. You see the list of people here. They're from all over the place. I mean, I'm from ENCCS, RISE in Stockholm. I have with me colleagues from ENCCS as well, but we've had trainers, teachers from Algorithmic in Finland and elsewhere, WACQT here in Gothenburg, Nordic Quest, what do we have more? Karolinska Institute, am I forgetting? Sintef, obviously. So it's been a very multilateral effort. It's been great, super interesting. So a big thank you to everyone, and a thank you to all of you here as well for attending and showing all this engagement and interest.
Right? Yep. Okay, so welcome back after lunch. So for the quantum chemistry, we have 2 notebooks. So one is from the previous edition of the school. So it was prepared by, I guess it was Veikko Palge that ran this session in the last edition. So this walks you through the implementation of the VQE, so with the fixed ansatz circuit and 1 parameter to optimize for the simplest case that you can think of. So the hydrogen molecule, which requires 4 qubits. No, well, 2 qubits. What? Like, how do you do it? Like this? No? Command plus? Command plus? No. Oops. I'm making it smaller and smaller. Okay. So this is the implementation presented in this 2015 paper, essentially. So as we were saying in the morning, for the VQE, you have essentially 3 parts. You prepare the initial state, which would be the Artifog state. You apply a parameterized ansatz and measure the expectation values. And then once you have the expectation values, you can use those to feed to a classical optimizer and propose a new value for the parameters. Now the circuit that we're going to use is very simple. So this is something that you can derive with pen and paper, the form of the circuit. And there is 1 free parameter in this circuit. So again, it's in principle a pretty easy thing to optimize, even by hand. But this shows all the very basic steps of running a VQE. So, okay, the Hamiltonian is given already in mapped form. So we already start with the mapping done. And then it's a question of essentially going through the cells and figuring out where code is missing. So instead of so there is the one parameter to optimize, and we are going to do a scan of the potential energy surface, so the different points in that binding curve of the hydrogen molecule, to see how the method performs. So, and this, so in the notebook, as you can note, we import the fake backend for the Helmi platform. So this can be simulated with the noise model that is provided by IQM and VTT. But in principle, as you've seen yesterday, you can also send circuits in batches to Helmi. The thing here that I haven't tested personally is how many shots you need to get a reliable error bar for the points, even though you're trying to optimize only a single parameter. So this is up for exploration, like how this actually performs on the 5-qubit machine. So this is nice because, of course, you can always go back to the paper and compare the results now in 2023 to what they published in 2015, if with the superconducting qubit machine that you have at hand, or with the different noise model, if things have improved or the results still kind of are affected by sort of the same error bar. And I'm not sure that, okay, correct me if I'm wrong, maybe you can try to increase the number of shots that you can perform on Helmi, and see how the error bar decreases, hopefully. Okay, so this is notebook number 1 on the basics of the VQE. And this one you can run on notebooks.csc.fi. And that's essentially how you can also get to communicating with the Helmi. And this one, I'll just put it in... okay, no, I cannot do it. So the second one, we're going to use a different online service to run this notebook, because this essentially uses our implementation of these adaptive state preparation techniques in our own package. So we'll put the information on how to access the platform on the HackMD. Many of you have already given me their GitHub handles, which is the thing that we will use to authenticate you there. If you haven't, just put it on the HackMD and I'll update the machine so that they let you in. So for the H2 example that we saw before, we were doing essentially what is called full CI, full configuration interaction, because we had 2 electrons in the minimal basis, 2 orbitals, so we can generate all possible excited determinants and have the full expansion in the Fock space, Hilbert space of the problem. In practice, this is something that even on a quantum computer would be really hard to do for any system of any size, because correlating all electrons and all orbitals is still pretty heavy. It would require a lot of qubits, which nowadays we don't have. And also, there's always a question whether to get that level of theory, an answer at the level of theory, whether it makes sense chemically, like does it give you any insight? So usually what chemists do is to restrict the number of orbitals and electrons that you consider for correlating. These are called active space methods. So you take a reference and then you select some subset. Okay, now it's smaller suddenly, but it fits with the other picture. So you select a subset of orbitals and a subset of electrons to correlate within that subspace. And within that subspace, you generate all possible configurations. And this reduces somewhat the number of determinants that you need to consider. Within the active space, if you do all excitation, is still a full CI type of method. So it's called a complete active space in that case. Still scales exponentially, but you are considering less electrons to correlate, which means less qubits. And this is in practice what we decide to do in this notebook, and what is practically done also in many other methods, even in classical quantum chemistry. So this is kind of the quantum chemical introduction. And then we will go through the adapt VQE, as Anton has explained. In adapt VQE, you kind of add one gate, or in principle, you can add multiple gates, depends on how you do it. But in the basic version, at every iteration, after you measure your state on the quantum computer, you get the gradient of the energy with respect to the active parameters. And you decide which other gate to add in the next iteration. So you expand the ansatz grows with every iteration. The links here are not working, sadly. And we will see how we can do this with the code base that we are developing. So here is a bunch of different molecules that you can try this on. Of course, you can provide your own molecule to try. The machines that this notebook is going to run on are not enormous. So, I mean, like trying to do a very large active space on a very large molecule will probably crash it for everyone attending. So be considerate. So we start with getting the I don't understand why it's going smaller and bigger, but fine. I don't think I need to understand that. So we get the molecular integrals from a classical program, and then once we have those, we can map the Hamiltonian. So we choose a fermion to qubit mapping. There are many of those, and I think here in the notebook we're using Jordan-Wigner mapping, but you can try any of the other that provided either by Qiskit or by our own library. This is an Evan mapper that uses ternary trees. And since we will be using either state vector simulations or positive operator valued measures, this POVM way of measuring that is informationally complete, you can add other operators without increasing too much the measurement overhead. And the other operators you can add to the optimization are either because you add them as penalty terms. For example, if you want to make sure that the eigenfunction that you get is an approximate eigenfunction of the spin number or the number operator, you would form this kind of Lagrangian so that you have approximate simultaneous eigenfunction of the two. Or also if you just want to monitor these values during the optimization of the state to see if you are actually converging to the right point. And then the important part in any adapt procedure, as Anton was showing, is what kind of pool of operator you want to choose from. So if you want to use these spin complemented fermionic single and double excitations, or something that is not spin complemented, so it might break spin symmetry but might help you with the convergence, qubit excitation based, and so on. So all of these options are implemented, so you're free to try any of those for the different problems. Of course, convergence might be faster or slower, or might not happen at all to chemical precision, depending on the problem and the pool. Because again, these are kind of heuristic constructions, so they're not foolproof. So in adapt, again, we start from the Hartree-Fock reference determinant, and that's, as Anton was showing, you apply X rotations to certain qubits to put them in the all occupied, the one state. And then, yeah, I mean, you can transpile the ansatz, look at it, and this will do the optimization of the state. And here you can choose whether to do state vector or POVM optimization, either with, deterministic simulation of these things by propagating state vector, or actually doing measurements with this informationally complete framework that we have developed. Okay, and then, I mean, the end of the notebook, it's a pretty long notebook, but if you get to the end, as I'm scrolling, you will see the output from the adapt procedure. So it will try to add gates until it reaches a certain threshold for convergence. And then from there on, you can plot again the circuit to see how many gates were added and in what form, and some stats for the calculations, so how many measurements were performed, in case you were using the IC-POVM framework, how the spin number evolves, how the number of operator evolves, and so on. And that's it for me. So I will lead the floor to the next introduction to a...
Great. Any questions maybe first?
Yeah, I forgot, sorry.
Yeah, one question.
Yeah.
Could you comment on the licensing model for this Aurora package?
It's not open source, and we haven't released it yet, even in closed beta. So you can use it on this notebook platform, but after the workshop, we'll revoke access. Yeah.
Hello. Hello everyone. Today, together with Björn Löfdahl, we prepared a hands-on tutorial which completely based on previous lecture and his article, this one, with more detailed theoretical description of each process. And this notebook is suitable for self-studying because it includes some concrete steps and descriptions. And first we will generate some data, and we are showing how we are doing this. So you know with what type of data you're working with. And for this tutorial, of course, we are using dummy data. Yeah, because with real data there are more complications. We simulate this data, store it in data formats, and store it in CSV file, and then eventually we can again extract it from the notebook. But if you will do this, you will need to define your data source. And then we can transform and inspect our data in this step and check a bit how it looks like. So for first part of this tutorial, we are going to run on state vector simulator. And that is why we generate a bit bigger data in this case. And we process, visualize it to get some insights from this visualization.
So yes, and here I can add that we have 100 age groups and 2 genders, and we can see if you go down to this graph again. Yes, we can see that we have simulated this data to have some sort of pattern that we can try to capture with our model.
Yeah, and after we have our data, we need to set up a kernel for this specific method, and that's what we are doing. And there you will have exercise 1, which you can just go through and consider to implement later on, because this exercise includes a bit modifications for kernel circuit. And current tutorial is based on this particular circuit, but for future experiments after we run the first part, you can try to do concrete steps to modify your circuit and see the results, because modifications to circuits in different ways, for example, we are adding new gates or changing gates, it's completely changing the Hamiltonian of algorithm of the system and how we analyze it. So that is why there is a place to experiment. And we a bit describe how step by step how to do that in efficient way, and as well some hints. And then you can test this code, but at the end of this notebook you will find solutions. But just first you can try on your own, and then if it's not going, you can check at the end of this notebook concrete solution for these exercises we have. And yeah, before in previous step we defined quantum circuit, and then we need to create quantum kernel function. And we are doing this. And at some point we can even draw our circuit, and we can see that we applied particular gates and applied particular measurement steps within our algorithm. Then we train our matrix, train our kernel on the data X we provided before. And this result similar to what you described during the lecture. So it looks very similarly to real implementations with real data.
Yes, so the first part then, it uses the state vector simulation to calculate the kernel matrix, so you get exact representation.
And here even a bit description broader what you can what information you can extract from this visualization and how you can analyze it. Because we are doing within data science visualization to get some insights. That is why visualization techniques are important and it's good when they're useful. And then eventually, after we defined our kernel function and circuit, we run support vector regression method, taking in consideration our data and kernel, and we are doing this in this specific way. And we also see score result, and it will be different each time, or how often would it be different?
In this case, it will be different each time if you do a new randomization of the data and generate new data. Then you will probably get a new score.
Yeah, if you run this notebook again later.
Yeah, but if you load the same data from a file, then at this stage you should be getting the same score.
Yeah, but just if it's slightly different, 1-2 points, it's not that influent, but just in case you can know, we are using random data, and that is why these values can be slightly different, but in a similar spectrum of pretty high results. And then we do some visualization of our processes, and we check the results against classical support vector model. And also we can check the score, compare our results. And then at the end, we also do analysis using scalar metric model. Maybe you can tell more about this.
For the next part here, we will do a leave one out cross-validation. So that basically means that we start with a full set of data, and then we remove one observation at a time. We train the model, so that we solve the support vector optimization problem on all the other data points, and then we try to predict the data point that we had removed. And then we iterate. We do this for each of our data points, and that will give us some out-of-sample estimate of how does the model perform. That is the idea.
And we do this in a few steps. And then we also visualize result and see how it performs and can compare our previous results, and a bit even here exists a bit discussion how we can validate the results we got and which method could be better and how to proceed, because when you create algorithm, it will not be, or when you run your code experiment using some kind of algorithm and particular model, maybe it will not be successful for the very first time. So you need to experiment within Jupyter Notebook environment, maybe change some parameters, maybe approach model in another way, because different scores and some of the processing of data and analysis provides you insight how you need to behave further and what you can do to improve your current solution. Also, we have a second exercise. Here is a bit just rendering not well, but in the inside notebook should look better. And we make it's a simple exercise with plotting some residual analysis, but also there are some concrete hints. And you have even advanced version of these residuals, but it's relatively simple code commands, and at the end of the notebook you can also find the answers. But it should be intuitive based on these hints to implement these exercises. And at some point, another part of our tutorial is to use, before we used state vector simulator for our use case, but now we are going to run on Helmi. And just classical steps. I think it's relevant to print topology and number of qubits coupling map of device, because this is very important for any type of quantum algorithm experimenting, is to understand with what type of hardware you are working, because each even 5-qubit computer, they could be very different between each other, because they have other coupling map, a bit another topology of these qubits, and even 5-qubit IBM computers, or they could be different. Or in our case, Helmi have IQM backend, and it could be different implementations of 5-qubit system.
Yes, and especially if you're experimenting with increasing the size of the quantum circuit, so increasing the number of qubits, then the how to do that in relation to what the coupling map looks like, that will impact the performance that you will get on Helmi, right? So it's important to keep in mind.
Mm-hmm.
Can I just mention one question here from HackMD? For this tutorial, will it be too big to run on my local computer? Should not.
No, you can perfectly fine to run it on your computer. Yeah.
Because it's native Qiskit state vector simulator. It's works perfectly on laptops and classical systems. And within this tutorial, we explore similar use case you did with real data. But of course, it's a bit simplified version of this, just to showcase how this approach and algorithm can work and what advantages it has. And as I mentioned, we again will simulate some data, and it's completely the same, it's just much fewer parameters, because Helmi hardware has a bit limitations, so we needed to a bit suit our process, and that is why we do even more simplified data example. But it's a similar approach as we used data for state vector.
Yes, so we can mention that. Now we're using still a very small quantum circuit in this example. The sample circuit is only 2 qubits, so that wouldn't be a problem at all to run on Helmi. But if we have too many observations, then we would have too many circuits to run on Helmi feasibly, because there's a limit on how many circuits you can have in the queue at the same time. So that is why we have reduced the size of the problem for the practical exercise here.
Yeah, but in principle, it's possible to utilize bigger data sets on Helmi if you have specific access to this system, which I think is possible to discuss for research projects with Finland group. And here we also visualize, and you see this data set is much smaller than the previous one, but it's similar approach. And on the graph, you see it's a bit fewer data points. So we do all the steps are similar. But here you have one exercise to implement quantum feature map. Here is, yes, almost everything already done, and you can just add one line. But as always, solution exists at the end. However, it should be easy logically to solve this without any solution. And it's good to visualize our circuit as well. And for this, for implementation on Helmi, we need to approach this implementation of algorithm a bit differently. We still do the same steps, but they just looks a bit differently due to another nature of quantum machine. And we do all circuits method, and because we need for a lot of circuits to execute.
Yes, so the difference here is that the quantum kernel method that we use for state vector simulation, that I think has been deprecated, so it doesn't work on physical hardware. So instead, what we need to do is that we need to manually create the circuit for each data pair, and that is exactly what this double for loop does. So it creates a circuit for each data pair, and then it transpiles it to fit on Helmi.
Yeah, within this function, it's not necessary always to transpile, but when we do transpilation, circuit would be more native to the system we are working with. So sometimes it's good to utilize transpiled circuit for particular backend, because backends are very, very different. And then we also execute our job in a batch mode because there are some limitations on Lumi, and even with such small example, we still need to do batch jobs, and it will take some time for you to execute, but we trace all the jobs, so you will see whether it works and where are you in the process, because I suppose if 10 people will run, maybe it will be a bit slower since we have queue. But you will see all the information within the notebook. And then we need to retrieve our job IDs, and it's easily implemented. And then we need to convert our processes data back to the matrix form, because to create these circuits and to analyze the data via quantum circuits and via these algorithms, we a bit modified our data and process it in a particular way. And at this step, we needed to get it back to normal state again, because before we doing this function, the data points is not connected as it should be reasonable for human understanding. You can, yeah.
Yeah, we can also add here the line here which calculates the frequency as rest.data.counts of 00 divided by n shots. If you recall from the lecture, we see that what we're trying to do here, we're trying to estimate the probability of measuring the ground state. And this is our estimator for that, right?
And we need to reconstruct our situation to having a good structured matrix of data, which we then will visualize, and this is the output. You will get approximately similar results. And can you please explain what we see on this diagram in comparison to state vector?
Yes,
output?
So now we have shrunk the problem size a bit, so I think that we have 20 groups in total, so 10 for each gender. So each sort of little box in the matrix, that would correspond to a kernel value of the matrix. Right. So on the diagonal we would have 1 values everywhere, and on the first and third quadrants we would have 0 or almost 0 everywhere. And we would have this same structure with decreasing dissimilarity whenever we get further away from the diagonal in the second and fourth quadrant, right?
There's a question here from our online audience which might be on the same topic. So could you explain a little further the Z kernel concept for running the quantum program? How does it relate to the SVR fit part?
Yes, so if we go back
here.
No, go back to the support, the state vector stuff. I think there it's just a little bit. Yes, here. So here we just name it the ZZ kernel, but that is just a name. And this part here, this is the function that I mentioned that was deprecated for physical hardware. So what this function does, the quantum kernel function here, is exactly what the explicit for loop did that we just show you. So this takes all the data that we have, and for each pair of data it calculates the kernel matrix. And then this matrix is used as an input, if we go a little bit further down in the code, to the support vector stuff, little bit, yes, here we will use kernel is equal to pre-computed, and we will use the kernel then, which is in the f_matrix_train variable. That is our kernel from the state vector simulation. So that goes into the support vector optimization.
Yeah, and then we will plot and analyze our results a bit more and compare them. And then we would like to process with error calculation at the final step of this notebook. And because, as you remember, for implementations on real hardware, we used smaller data, then we need to redo similar steps with this kernel because it take into consideration data that we redefined. So to compare errors, to compare results from Helm implementation and classical and state vector simulation, but on the same smaller data, that is why we need to redo this step for purposes of comparing. And then at the end, we will get this output, which I think would be.
So this graph, it just, if we go up to the cell with the code here, yes, we take errors. This is defined as the absolute value of the difference between the kernel that we got from Helmi and the kernel from the state vector simulation, now in the reduced form with fewer groups. So this error matrix here that we are displaying, this is just the error that we get between the Helmi implementation and the state vector simulation displayed per cell in the matrix.
Yeah, so that's it. Good luck with this tutorial, and do not hesitate to ask questions personally or in HackMD, and we will try to help with this. Thank you.
Yes. So the tutorial is not quite at the right place yet because we had some dependency issues, as you usually do. So I'll do it from my computer, and I hope a new version of it will soon be in the right place. So here it is, protein folding with QAOA. It's built in a way so you can basically do it from top to bottom. There's not too many tasks that you do yourself. I more put it like all the code there so you can click around and kind of change and explore more with it. It starts off quite basic and then it explodes at the bottom and you get to do something fun, hopefully. So there's there's a quick overview. There's probably a lot of like repetitions. Oh, the whole screen changed. But basically, we have an energy function that we want to minimize with finding the best solution given the energy function. The energy function is taken straight from this publication. So the question earlier, maybe this person is not here anymore, about the quantum annealing for the protein folding. It's this publication by Ebba et al. And I've taken their energy function, and basically this is like the QAOA version of it. So it's heavily based on their code and me rewriting it. So I recommend looking at the publication, but you don't need to have read the publication in order to be able to go through it. The quantum computing part uses PennyLane instead of Qiskit, which is, well, it looks quite the same. So we have a bunch of imports, and then we have the protein model. So it is the coordinate-based HP lattice model. So we have the energy function, as opposed to do here, is the interactions between the amino acids, H and P, if it's H or P. And then we have 3 penalty terms for the 3 constraints of not overlapping. Have I presented all of them? So we have 3 constraints. We have don't place the same bead on 2 different spots. We have don't have 2 beads on the same spot. And then the last one is make sure that they are in order. So we don't put bead 4 after bead 1. And all of these has a penalty, like a Lagrange penalty term. You can play around with these. I've given you the best ones. You can use the best ones, and the best ones is from Anders' paper. We can take this whole advanced big energy function and we can rewrite it very much easier in the QAOA format of we have the one-body interactions here, and then we have the two-body interactions. And the two-body interactions is basically the thing that we need, mostly. So the new version with the dependencies has a big block here where I copy-pasted a lot of code. Just scroll by it. If you use the GitHub instead of going through the website, you won't see this block of ginormous amounts of code. So it's basically a class that hides all the math, so you don't have to poke around in it. So let's go for a walk together down Penny Lane. Yeah, it's a lot of math. Yep. And then there's some nice functions for plotting and so on and so forth. Yes. And now we're at the bottom. Whoa. Yes. So we feed in a sequence. You can test different sequences, but I've chosen HPPH. So we have 2 hydrophobic and 2 polar beads. Here is a 3x2 lattice. And here is a lambda vector, which is the penalties. So I've taken the best one from the paper. And then we create a instance for the protein. And if you have an instance for the proteins, you have everything like put together. So for examples, the bits, like which qubits is going to be what, is going to be on the format of what coordinate it has on the grid, and then which index it has in the sequence. So we can print out all the names of the qubits. So this is like 1 qubit. If it's turned on, then the first bead is placed 0, 0 on the grid. We have our 2-body matrix and our 1-body matrix that we need to build up the Hamiltonian later on. For this encoding, where we have a 3x2 4 amino acid sequence, we need 12 bits. And we can say how big is the solution set compared to the feasible solution set compared to the total solution set. It's 34%. And why do we care about this? Well, we want to make sure that the QAOA performs better than the random guess, and this is the random guess. We have a way of like printing out and seeing the different folds. So we have some functions for doing that. We can print out the whole thing. Let's not scroll through that. And then we go to the QAOA. It's a small rundown again. You can go into the demo of how to use Penny Lane if you want to know more about it. But we basically take the energy function above with the 1-body interactions and the 2-body interactions, and we build our Hamiltonian. So we have the cost part, which uses the 1-body interactions and the 2-body interactions. As such, we then translate all the bits into qubits, and we can print out our Hamiltonian, which we can then feed into our QAOA. Here is a function that figures out the ground state. It's a cheat function. It goes through every single solution and asks what's the energy of this. Why do we do this? Well, for benchmarking, to seeing how well did we perform. Because this is a toy model. So if you give it too big of a lattice, or if you give it too big of a thing, this is gonna take a while. So if you get stuck, it's probably here it's gonna get stuck. Because it's not an effective function. It goes through every single one just because we want the answer. I have then implemented a very easy X mixer, and then everything goes into the QAOA. Here's a description of how to build up the circuit. And then after this, you'll see different functions of how you optimize the circuits and so on and so forth. But I do think it's better that you go. So this is like the basics. You have one thing at a time. If you go with the on the website, you'll have to go downwards, and then you'll see the rest of the code. But there's also a GitHub that has everything you need on it. Yes. Any questions?